Okay, today's lesson we're going to be working with volume again. So the previous lesson we worked with volume of a disc and volume of a washer. And then today we're going to be doing volume of a cylindrical shell. And so it's kind of like, um, first of all, let's just talk about the shell. So volume equals 2 pi, the average radius, times the altitude, which this is the height, times the thickness. So if I had a particular shell here, and I took this and rolled it out, we can see that this would be my 2 pi r. This would be my height. And over here is your dx. So we can see that that's where this formula comes into play, where if you have the radius we're going to look at is going to be this value in between here. Our height is our value there. So by the definition, like we've done before, we said if we're willing to take many of these, and as they approach zero, like get smaller and smaller and smaller, that we can actually get the volume. And it's denoted by 2 pi x f of x dx. In this case, this is your radius, this is your altitude, this is your thickness. So let's just take a minute and say, well, why are we going to do shells? If we have a disc method and we have a washer method, why would we need to do a shell? So if we think back to what we did previously, if I was given this function, which is the blue graph, okay, I was given y equals 0, x equals 0, x equals 2, and I asked you to revolve it about the y-axis, right? So right here, we can see that and remember for disc washer method, if my axis of revolution was given to me, my representative rectangle would be perpendicular to that. So let's just say right here I chose this to be my rectangle. So I label it dy. Now I know that if I was to revolve that dy, I would get a CD type. So that's going to be, it would have a hole in it right there. Okay, this would need a washer. And if I was to put my representative rectangle down here, it's also a dy, but would it have any gaps in it? No, it wouldn't have a hole in it. So this would be, in the case, that would be like a disc. So we could see if I gave you this particular problem and only having the disc washer method, that we would have to do the washer method here and the disc method here, and then do what to them? Add them together. Good. So we can see today, if I was to draw a shell, and if it helps to think about it like a toilet paper roll, and we had infinitely many of those, then in stackable, there's actually a really good picture of this in your textbook um, to get a better visual of that on page 323 if you want to look at it. But anyway, so you can see here we would have 2 pi times the radius times the height times the thickness. So in this case, we would just be able to set it up and calculate this expression, this integral here. So the next thing we're going to do is take some time and actually work on how to calculate these. Okay, so let's just go ahead and work this one. First of all, we have our 2 pi, which we can bring this out front if we prefer to do it that way. This next thing is our radius. Now right here you can see where I've drawn. So if I let my representative rectangle be here, this green one, then it's a dx. Okay. Also, let me back up and say for shell method, the rectangle's parallel to the axis of revolution. So if this one they told us to revolve about the y-axis, we make a parallel rectangle. And so I label that one dx. Okay, so that becomes our thickness, is our rectangle. So that's dx. That also tells us that all of our variables need to be, all of our expressions over here need to be in terms of x. So now the radius from here to this representative rectangle, we're going to say is x. So that's going to be our radius is here. Now the height, or the altitude, is just going to be our function, right? So it's described by that blue equation, which in this case is x squared plus 1. So at this point, we're able to just use, evaluate this. So let's go ahead and just multiply this out. I'm going to go ahead and pull the 2 pi out front and multiply this out, and then use the fundamental theorem of calculus to solve this, and then check your answer. also, before you do that, your intervals are also going to be, if this is all in terms of x, your representative rectangle is dx, then your interval values are going to be the x values. So, okay, so simplify the algebra there, and when we calculate this, we'll evaluate it from 0 to 2, and we get 12 pi, which is approximately 37.70 units cubed. Okay, let's just see another one set up and find the volume of the resulting solid. So what we would have over here, if we were given this function y equals 2x minus x squared, and they tell us to revolve that about the y-axis, the first thing I'm thinking is, this is shell method. They told me my axis of revolution is the y-axis, so my representative rectangle must be parallel to that. And the first thing I do is I label that a dx, because the dx tells me, it sets the stage. All of my interval will be in terms of x, my thickness will be dx, and also my intervals will be in terms of the x values. So that's the first thing I kind of make a note of. The next thing, this is just kind of a very descriptive image of what's going on. Now, we're going to take some time in just a minute to stop and just do a side little note about naming the radius, but for now, let's just say, if I let my representative rectangle be here, then I'm just going to let from here to here be x, okay, because it's relative. Because what we can do is just, our rectangle can be anywhere. One student can draw their rectangle here, another student can draw their rectangle here, and it doesn't really matter. We're going to say from the axis of revolution to our point on the graph that we're going to have in mind is going to be our x, our radius. Like I said, we'll spend some more time with that in just a minute, but thickness of the shell would be dx, that's determined by your rectangle. The radius is going to be your x. The height is that point where the function touches the top part of the graph. So in this case, it would be your 2x minus x squared. And then, of course, your volume by your formula in your previous page over here. Okay, it's given up here for a cylindrical shell, and it's also down here in our integral format. Okay, so on this next page, I just basically work through that just like we did on the previous example, and you multiply this out algebraically, and then afterwards take the antiderivative and use the fundamental theorem of calculus to get your volume. So if you want to take a few minutes, you can attempt to work that one on your own. Okay, and because I know the radius is something that you're going to have a question about, let's just kind of veer off for a minute and discuss the radius. So let's just pretend I was given this particular function. Let's look at this graph first, okay? And it was revolving about the y-axis, so let me go ahead and sketch that in here. So if it was told to me that was revolving there, and I know I'm working with shell method, I'm going to draw parallel to that axis. So I know I'm working with a dx. But first of all, this x, this representative rectangle, one person can draw here, someone can draw here. So basically we just say this is x. Okay, now let's say if I ask you to draw it, let me pick a different color. Let's say if I said, well, the axis of revolution, let's do 3 first. Axis of revolution is here, and I give this to you. Right? Then basically my shell would be revolving around that. So if you visually can see that, then you will be able to see that from here to here is how many units? 3 units, good. So, and if from here to here is going to be, what would you have there? X, right? So then what would you say about my radius of, if I revolved around here, what would be my radius in red? 3 minus x, right? So we could see that this would be the 3 minus x. Well, that's what I'm denoting down here. Okay, that would be if I given you a axis, a revolution to be x equals 3. Now, let me erase all that stuff and say, okay, what if I ask you, if I gave you your axis of a revolution over here at x equals 1, then you can see that my radius, if I revolved it around this axis, then if I drew my toilet paper roll here, right, then I'm looking for radius from here to here, which would be from here to here is x, and how many is here? 1 unit. So what's x minus a negative 1? X plus 1. So that's just so that you can see it there. All right, let's look at the next one. So same thing. What if I have okay, so if you drew the axis, if I had given you the axis of revolution here, then my radius would be what? X minus a negative 3 again, because from here to here is x, and then from here to here is 3 units, which is x minus a negative 3 if we use the values, but this is actually just going to be x plus 3. So you can see that there. Okay, and if I gave you axis of revolution as x equals 2, then from here to here is x, and from here all the way to that is 2. So my axis of revolution, my radius for my shell right there would be 2 minus x. Okay, and likewise over here, if I had an axis of revolution at x equals 3, you can see that the radius would be the x minus a negative 3 or x plus 3. And also, if I, just like the other two cases, drew an axis of revolution around 2, then the radius here would be 2 minus x. Like I said, those take a little bit of time to get used to. And so this is just, we label that x in terms of our radius, and then we just account for that in respect to whatever your axis of revolution is given.